Hello there, and welcome back on LabHub. So in this video, we're gonna talk about the Ampere's law. So imagine some current. Imagine a wire with a current in it, right? And according to our knowledge about electric fields, magnetic fields, what will it induce? Right, it will induce a magnetic field around it. So we can also represent a magnetic field, like sum of magnetic field and distance of magnetic field travels, like this. So this is the general formula of Ampere's law, which states that sum of magnetic field and the distance where the magnetic field travels equals to permeability of free space times total electricity current passing through the surface bounded by a loop, like this loop. And in our case, this is induced, right? And we also need to know that the magnetic field, according to the right-hand rule, right, it induced at first because of the right-hand rule. And it travels in a circle, like this, like I represented here. And it always travels as a circle, in a circular motion. And here is the current enclosed by this magnetic field, right? So then we can represent it just like this. Oh, sorry. Sure. And in our case, the length, like the distance, the magnetic field travels is equals to C, which is basically 2πr. So then the formula is 2πrb equals to this, right? And now we can find a magnetic field itself. So again, a magnetic field always happens around a current, like a wire. This is a wire, and it moves some current upwards, right? So around the current, there is a magnetic field according to the right-hand rule. We learned it in an electricity course. And we can find the sum of the magnetic field, right? The sum of magnetic field and length where it travels like this. Like permeability of free space times induced current. And the permeability of free space is a constant. So we need to know that it equals to 4p times 10 in negative 7. Now let's talk about the solenoids. A solenoid is a really scientific name of really simple stuff. It's just a coil of wire. So this is basically a solenoid. And there is some current passing through the solenoid. And according to the Ampere's law, there will be a magnetic field around it. Right? So we'll go this way. And outside the solenoid, the magnetic field is very weak. So at this point, right, at the center of solenoid, the magnetic field is really strong. But even at this point, it's not gonna be as strong as it could be. Or even here, it's way slower. Here, it's way more slower, and here it's 0. So how can we calculate the magnetic field in that case, in solenoid? Let's draw a new one. And to find a magnetic field, we need 4 points of our rectangle. Let's call them A, B, C, and D. Right? So therefore, the sum of magnetic field and the length will be magnetic field length times AB plus magnetic field L times BC plus magnetic field length times CD and plus magnetic field length times dA. Really long formula, but here's the thing. AD and CB are parallel to the source of magnetic field. So they are basically equal 0, right? So we got a AB that's something, we got a BC that's 0, like X, 0, then we got a CD, we'll figure out about it later, and we got a dA that also 0 because it's perpendicular to this stuff, to the source of magnetic field. And now, according to this thing, again, what is the DC? Try to guess. Yes, it's almost 0. So it's approximately 0 because it's on a long distance from the center of the magnetic field, from the center of the source of it. So then the formula is the sum magnetic field L equals to X, which is BL times AB, no, just a BL, plus 0, plus 0, plus 0. So this is the formula. Yeah, we can just erase it. And the formula like this. Oh, without this stuff. So this is the original formula. And we will use it really a lot, I would like to say. And the BL, not the L, the BL equals to this. This is induced. Oh, enclosed. I'm sorry. Enclosed current. Right? So now, let's figure out what is the dependence of amount of wires, like amount of loops in a wire. And then estimate maybe formulas that could be easier to use in your problems. Yeah, with this kind of problems. So when we got a one loop and the current here, like the current going through this one equals 10 amperes, 10 amps. What if there's a two loops? What is the current? The current is 2 times bigger. So this is 20 amps. So the current depends on amount of loops, because the current flow around the loop twice in that case. Right? So here the current goes around the loop twice, and therefore the current is 2 times more. What if there's 3 loops? Current equal 30 amps, because the current flows around the loop 3 times, etc. And now we can estimate the amount of loops. N is amount of loops. So here n equal 1, here n equal 2, and here n equal 3, because here is 3 loops. And what can we do with that? Maybe we can use it in a formula. Yeah, we easily can. And we should do it, because the formula of enclosed current that we used in a previous formula right here is equal to N times current, times all the current passes through the wire, right? And now, therefore, the BL equal to this. And if we need to find exactly the magnetic field, we should divide everything by L. And then we got the magnetic field equals like this. Maybe we can make it a bit prettier. Like, I don't like this stuff. I don't like to watch this. This operator like freaking me out. I don't want to see it. And yes, we actually can. Because small n equal to a big N, which is the amount of loops, divided by L. And this is loops per meter. So this is the amount of loops we got per meter. And then the magnetic field equals this. And it works basically in a solenoids. So magnetic field is a permeability of free space times loops per meter times current. Current that passes through the loop. And this is basically all you need to know about Ampere's law.